Hi everyone. For the past couple of episodes, we've talked all about the inner product. This episode, I want to introduce another fundamental object in quantum mechanics, the bra. I also want to really dig into bra-ket notation and justify my previous claim that it is incredibly powerful and useful. So, to begin introducing bras, let's look at an example in the vector space of R2. I'm going to define a very simple linear map called Lx. What it does is it takes in a vector and spits out whatever its x component is. So, this vector has a component of 3 along the x direction, so this map would return 3. This vector has a component of -1 along the x direction, so this map would return -1. You can check that this indeed is a linear map. In other words, it satisfies the following properties. Now let's understand what this linear map is doing. Fundamentally, this map takes in an element of our vector space and returns a single scalar number. We have a special name for maps that do this. They are called linear functionals. Formally, a linear functional is any linear map L that goes from the vector space to a scalar number, which may be real or complex. Basically, it's any linear map that takes in a vector and spits out a number. Now that we know what a linear functional is, let's move back to R2 and figure out what the matrix for Lx looks like. I encourage you to try it out on your own before we run through it. Now, that being said, we know that Lx takes us from 2 dimensions down to 1 dimension, so we know we have a 1×2 matrix. The first column tells us where the x basis vector goes. So, plugging in 1, 0, which has a component of 1 on the x-axis, we get a 1 in the first column. The next column tells us where the y basis vector goes. So, plugging in 0, 1, which has a component of 0 on the x-axis, we get a 0 here. And this is the matrix of this linear functional. So we see that we get what's called a row matrix. It's essentially a column vector on its side, and what it does is it takes in a column vector and spits out a number. Now, let's take a step back. Remember that in R2, a linear functional is a linear map that takes us from 2 dimensions to 1 dimension. By definition, this means that all linear functionals in R2 are represented by 1×2 row matrices. So the set of all linear functionals in R2 consists of the set of all row matrices. Much like column vectors, this set of all row matrices actually forms its own vector space. Seriously, check all the conditions, they work. This vector space is known as the dual space. Hopefully you see why it's called a dual space. Take your vector space of column vectors, turn them on their side, and what you get is the dual vector space of linear functionals. This has been specific to R2, but the dual space is a very useful concept in abstract vector spaces. Formally, we define the dual space as follows. Given a vector space V, the dual space V star is the vector space of all linear functionals in V, which remember are just maps that take in vectors and spit out numbers. So all linear functionals L live in V star. Although this is an abstract definition, keep the intuition that the dual space is analogous to the space of row matrices. Now, I remember when I first learned about functionals in the dual space, I thought it was unnecessary for quantum physics. But think about it. Our goal is to build a mathematical model for the real world, and in the end, we want to be able to extract values and predictions from it. For example, given our quantum state, say we want the probability of getting an energy of 3 electron volts. Or, say we want the average position we expect in this state. To get these, we have to go from quantum state to number. And so we know that a linear functional is involved here somewhere. So hopefully you're convinced that we have to use linear functionals in our quantum theory. In fact, linear functionals are so important that we will ascribe a special symbol for them in quantum mechanics. A symbol called a bra, written as a backwards ket. Remember that this is a linear functional, so this should be seen as an operator that acts on a ket and returns a number, possibly complex. As we stated before, these bras live in the Hilbert dual space. That being said, you may be noticing something. When we put a bra and ket together to get a number, it looks suspiciously like an inner product in this notation. Yet we have made zero mention of the inner product. So what's going on? To begin solving this puzzle, let's go back to our LX operator in R2. Take a second to notice how LX acts on a column vector. Do you notice how it is as though we are taking the dot product with the x unit vector? In fact, when a linear functional in R2 acts on any vector, it can be written equivalently as a dot product with the corresponding column vector. This is actually a very deep and general mathematical fact, rooted within something called the Riesz representation theorem. This sounds kind of daunting, but it's just a theorem about what we discussed. The theorem states that for any linear functional L phi, the action of L phi is equivalent to taking the inner product with some unique vector phi. I won't prove the theorem here, but there are a slew of internet sources that have given rigorous proofs if you're interested. So, in our R2 example, this unique vector was 1, 0, and acting with the LX operator was equivalent to taking the dot product with 1, 0. And now hopefully you see why we chose our suggestive notation for a bra. A bra is just a flipped ket because the action of the bra linear functional is mathematically equivalent to taking the inner product with that ket. This notation for bras, kets, and inner products is collectively known as bra-ket notation, or Dirac notation, as he was the first to use it in quantum mechanics. So why is this notation so powerful? As you can see, it has the Riesz representation theorem baked right into it. You can break apart inner products and put together bras and kets however you please, and you can be rest assured that whatever you get still makes mathematical sense, all because of the Riesz representation theorem. I mean, really think about this. Although a bra and the inner product are formally completely different mathematical entities, bra-ket notation makes their connection absolutely seamless. But remember, the Riesz representation theorem is working hard behind the scenes. As one of my undergraduate professors used to say, let bra-ket notation do all the work for you. To really show you the power of bra-ket notation, I want to run through a quick example. Let's say we have an orthonormal basis in our vector space, and we expand an arbitrary quantum state in this orthonormal basis. Remember from chapter 4 that because all the states are orthonormal, we can calculate the coefficients as follows. It's also really easy to prove this yourself. So let's plug in this expression for all the coefficients. Now let's move the inner product to the front. Here is the power of bra-ket notation. We can break apart the inner product. So now we have this operator being applied to the ket psi. The ket psi is the same for every element of the sum, so we can pull it out of the sum. Now take a look at the right-hand side. We have a summed operator that, when acted on psi, returns psi. This means that we have just proven that for any orthonormal basis, this sum must be equal to the identity operator. This expression is sometimes called a resolution of the identity. Now, there's more to say about this, but for now, take this as a cool mathematical insight. More importantly, note how bra-ket notation made it really easy to move things around. If you run through this derivation in traditional vector notation, you'll very quickly see how clumsy and unintuitive it feels. With that, we have all I wanted to say about bras and bra-ket notation. Throughout this series, I encourage you to take a step back occasionally and ask yourself, how would I do this in traditional notation? Once you do that a few times, you'll be thankful for bra-ket notation.